Hi everyone, my name is Marco Marengon, and today I will tell you something about the three-dimensional sphere. So before I start, maybe I'll say a couple of words about myself. I'm a mathematician. I'm originally from Italy, and then I studied in England, in London, and I have worked in the US, in Germany, and now I'm working in Hungary, in Budapest, which is where I am recording this video right now. What I wanted to tell you about is the three-dimensional sphere. In mathematics, we call it S3 usually. Everything has a name. And before I start, I want to caution you. I want to tell you that what you may think of as the sphere is not what we mean here. So the usual sphere, the one that I tried to draw here, is actually two-dimensional. We will go over this in a second. So this is not the sphere that we're talking about. All right, so let's get started. And the first thing I should tell you is what I mean by dimension, because maybe now I am confusing you because I have told you that the sphere that you're used to is not the three-dimensional sphere. So I will not give you the precise definition of dimension, but instead I will give you some ideas and some examples, which usually work better. So I will start with dimension one. The prototypical mathematical object that has one dimension is the line. So let's suppose that we have a cockroach and we force the cockroach to live on this line that I have drawn here. Then the cockroach can go only in one direction. It can go basically just along the line, forward or backward along the line. But we treat forward and backward as the same direction. So in this case, you see that there is one line of direction in which the cockroach can move. Sorry, here I meant to write the cockroach, not you. I'm not implying that you are cockroaches. So there is one line of direction in which the cockroach can move. And so we say that the line has dimension 1. We give a name to the line, we call it r to the power of 1. Let's give another example of an object that is one-dimensional, and that's the circle. We call it S1 as well. Here I have to be careful, I have to say exactly what I mean by circle. By circle, I mean just the boundary, not the inside. So the inside is not part of the circle, I'm not considering it. Then, if I am considering only the boundary, I can play the same game as before with the cockroach. I force the cockroach to live on this mathematical object, that is the circle. Again, only the boundary, not the inside. And then what happens is that locally, the cockroach has only two possible directions in which it can move, like forward and backward. But again, we treat forward and backward as the same direction because they are on the same line. So this is what happens locally. Locally, the circle looks like a line. And so this is why we say that the circle has one dimension. Or equivalently, the cockroach can move only along one line of directions, back and forward again. Let's move to the next case, which is dimension 2. And here, the prototypical example is the plane. So in the plane, your favorite cockroach can move not only back and forward, but also left and right. So there are at least two lines of directions in which the cockroach can move. So it's become smarter. And in fact, there are infinitely many lines of directions in which the cockroach can move. For example, the cockroach could move diagonally. Oops. Like this. But a diagonal movement can always be realized by moving first in the left-right direction and then in the forward-backward direction. So in order to do the diagonal move, we can move first to the left and then up. And for this reason, we say that this diagonal direction is not a new independent direction in which the cockroach can move, but there are only two independent lines of directions in the plane in which the cockroach can move. There's back and forward and left and right. And all the other directions you can recover by just combining these two directions. Let's see another example, another example of a mathematical object with two dimensions is the sphere, where here by sphere, I mean, as before, only the boundary, not the inside. So if you consider only the boundary of the sphere, then locally, the sphere looks like R2. It looks like the plane. And so again, we have that locally there are two independent lines of directions. And so again, we say that the sphere is two-dimensional. So this is the usual sphere we are used to. It's like, it's basically a Pokeball, but without any Pokemon inside because it's empty. And we say that it is two-dimensional because the boundary only has two independent directions. So what we are somehow seeing here is that the dimension somehow counts the number of lines of directions in which you can move independently. So let's go to dimension 3. And in dimension 3, we only have one example that we are familiar with, that is the space in which we live. So now we have our favorite cockroach that can move in the plane as before, so forward, backward, left and right. But now we endow our cockroach with a jetpack, and so it can move also up and down. So now it can move all through all of space. And so there are three independent directions in which the cockroach can move. And so we will say that the space has dimension 3. Fun story here, I tried to Google cockroach with jetpack, and to my amusement and simultaneous disgust, there are actually images of that. So if you want, you can try. So here we have the space as an example, we call it R3. And you may have noticed that there is a pattern. We have R1, the line in dimension 1, R2, the plane in dimension 2, R3, the space in dimension 3. And then we have S1, the circle in dimension 1, S2, the sphere in dimension 2. So the question is there an S3? And, I forgot, yeah, sorry. Is there an S3? So a three-dimensional sphere where locally there are three independent lines of direction? And the answer is yes, there exists such a mathematical object. And now the question is, can we somehow visualize it? So this will be essentially the rest of this talk. All right, in order to visualize the three sphere, I will first tell you how you can visualize the circle. So starting from the real line. So we will use a concept that is called the stereographic projection. And the key idea that I wrote here is that the n sphere, so the circle, the sphere, or the three sphere, can be viewed as Rn plus a point at infinity. So let's see what I mean by this. I will start with dimension 1. I consider the real line, the line R1 that we mentioned earlier, that is one-dimensional. And now let's pretend that this line is made of some elastic material that has been stretched to infinity. And now I I release it. I release this line, so it will contract. And let's say that when it contracts, it somehow contracts so that the two endpoints that are stretched at infinity meet each other at this point that I labeled infinity in the picture here. So somehow I am releasing this infinitely stretched line, and what happens is that it wraps over this circle. So this is the operation that I'm doing. I wrap the line over S1 so that the two ends of R1 that are at infinity do not touch each other. So they just go to the point at infinity, but they do not overlap. So that one point at infinity is not part of the line, and we just add it artificially. So I'll give some more another picture of this because I realized that I'm not being very good at explaining it. So let's consider the part of the real line that I'm highlighting right now. Then when I wrap the line over S1, I want the highlighted part to wrap over this bit of the circle. So let's do something else. So something like this, for example. Then here I have another part of the line that goes further away outside of the picture so that we don't really see it. And this part we wrap over here. So overall, I am wrapping all the line onto S1, leaving the point that I labeled infinity out. But in doing so, I'm not preserving the distances. So this is something that I want to mention. Here you can see that the distance that you have on the line here is much longer than the distance that you have on the circle. So this is why I mentioned that I pretend that the line is made of some elastic material, because I want it to shrink while you wrap it up over S1. So if this was really confusing, I apologize. The takeaway is that we can envision S1 as the line wrapped up plus the point at infinity. So this is all you have to take away from this slide. So now let me go to the next. The next slide is the same, but in dimension 2. So in dimension 2, we have a plane and the usual sphere. And again, we want to wrap the plane onto the sphere like an Easter egg. So the plane is the paper in which you're wrapping your Easter egg, and the sphere is the Easter egg itself. And you wrap the plane onto the Easter egg, onto the sphere, again by leaving out one point, this point at infinity. So here is another picture that I drew. If you take a portion of the plane between two concentric circles, like the one that I drew in pink here, then this is going to be wrapped onto a horizontal slice of the sphere. So again, this wrapping doesn't preserve the distances. So you're not wrapping with your usual piece of paper, but you're wrapping with some very fancy material that is elastic and somehow shrinks as you wrap it over the sphere. And again, the thing to take away is that the two sphere, S2, is made of the plane, R2, wrapped onto the sphere, plus the point at infinity that is left out. So here I'll take a little break, and I want to just give a quick explanation of why the name for this interpretation of S2 or S1 is called projection. It's called stereographic projection. And the reason is that this identification can be envisioned as a projection of the sphere onto the plane done from the point at infinity. So I prepared myself, I looked it up on the internet. This is an illustration that I found of the stereographic projection. So here you pretend that there's a source of light at the point at infinity on the sphere. And that that source of light projects anything that is on the sphere onto the plane. And so whatever is onto the sphere casts some shadow on the plane. And this is the way the shadow is cast onto the plane. So this is an alternative way to the one that I described of wrapping the plane onto the sphere. So the other way around is that you take the sphere and you just project it onto the plane by casting its shadow onto the plane. And here you see again that not only this identification doesn't preserve distances, it doesn't even preserve straight lines, because a straight line that is on the plane that you see here is identified with some curved line on the sphere. All right, let's go back to the presentation. So we mentioned that S1 can be envisioned as the line plus a point at infinity. S2 can be envisioned as R2 plus a point at infinity. So maybe it will not surprise you that by analogy, we can envision S3 as the space R3 together with a point at infinity. Now, of course, since the space already takes all of our imagination, we can't really think, we can't really say where the point is, because somehow the space has already taken all of our brain. So we have to imagine that there is another point that we don't know where to place, but somehow, if you go far enough, if you go at infinity, in any direction, you will go to this point at infinity. So if you go far enough in any direction, you will go to the point at infinity on the free sphere. And I want to give you also an example from the literature of my culture, from Italian literature, of a sphere, of this three sphere. So following Florensky, there is a reinterpretation of Dante's cosmology as a three sphere rather than just a three space. So how does Dante's cosmology work? There's Earth, and then hell is envisioned in Dante's comedy as a hole pierced inside Earth of this kind of pyramidal shape. And then purgatory is just another pyramid that sits on Earth on the other side, on the opposite side of hell. And then all around Earth are the various spheres that make up paradise. So the heavens are concentric circles that are one inside the other. And now, at some point in the comedy, Dante explains that in order to go to God, you just have to pass all the heavens, all these spheres, and then no matter where you will go out, you will eventually reach God. So somehow God is in a point that you can reach by going far enough, but in any direction. So using the interpretation of a sphere of S3, of the three sphere as R3 together with a point at infinity, we can envision the space as hell, purgatory, earth, and the various spheres. And then the point at infinity is God that you can reach by going in any direction far enough. So this interpretation of Dante's cosmology, I think, dates back to Florensky first. This is as far as I know. Okay, so now before concluding, I just want to mention one more thing. That is that somehow all the spheres that we have talked about, the circle, the sphere proper, and the three sphere, seem to live in some other space. So let's consider the circle first, S1. This is a one-dimensional object. We mentioned that locally you can move only along one line of directions. But in order to see it in its entirety, you need to go to two dimensions. So to see it in its entirety, you need to see it in the plane, which is a two-dimensional object. So we see that in order to see a one-dimensional object completely, we have to go one dimension up. And for the sphere, the same happens. So the sphere is two-dimensional. Again, it's just the boundary of the sphere. So it is something that locally looks like a plane. But in order to see it completely in its full, we have to go to the space. So we have to see it as sitting in the space, which is three-dimensional. And this is maybe the origin of the confusion that I was mentioning at the very beginning, that we're not used to thinking of the sphere as a two-dimensional object. And now let's move to the three sphere. The three sphere is defined as a three-dimensional object. And now you can imagine that if you really want to see it in its full entirely, so not just as R3 union a point at infinity, then what you need to do is to go one dimension up. So you need to go in a four-dimensional ambient space that we call R4. And now I will not delve into R4 too much because that's not the object of this short lecture. But maybe I will give some hint to what it is. So one question that sometimes I receive is, what is this four-dimensional direction? We mentioned earlier that the dimensions are somehow the number of independent directions in which you can move. So you have forward and backward, left and right, up and down. What is the fourth one? And one way to visualize this fourth dimension is time. So in addition to the usual three lines of directions, we add time. So we endow our cockroach not only with a jetpack to move up and down, but also with a time machine to move forward and backward in time. And this adds an extra direction in which our cockroach can move. Of course, this is not as intuitive as the plane and the space, because we're not really used to think of time as a dimension. So it's maybe just an analogy. So to conclude, I just want to say that I didn't find a good image on Google of a cockroach with jetpack and time machine. So maybe this could be an exercise for you. Thanks very much, and good luck with the project.